Welcome. Today we're doing a deep dive into something we all experience, but maybe you don't fully understand. The arrow of time.
Right.
There's this central paradox, You can watch a video of planets orbiting and play it backward. It looks totally fine. The physics works both ways.
It's time symmetric,
But
exactly.
a video of an egg cracking, if you play that in reverse, it feels fundamentally wrong. Things break, they don't unbreak. So why?
Well, the short answer, and it's one of the most solid laws in science, is the second law of thermodynamics.
Entropy.
Entropy.
Right.
It dictates that in any closed system, the total amount of disorder or entropy is always increasing. That one-way street, that slide into messiness, is what we perceive as time moving forward.
Okay, so that's our mission for this deep dive, to understand why time itself is defined by this move from order to, disorder.
Exactly.
So to really get the mechanism, we need to think about the numbers. The sources used a great example. A deck of cards. An ordered state, low entropy, is that deck stacked perfectly. Aces through kings, all suits together. Very low probability of that happening by chance.
Right. There's really only one way for it to be perfectly ordered. But disorder, that's the shuffled deck. And the thing is, there are just trillions upon trillions of ways for a deck to be messy.
So the universe isn't pushing things toward disorder.
Not at all. It's just that disorder is a fantastically more probable state to be in. The system naturally wanders into the state that has the most possible arrangements. It's just statistics.
So wait, this is where it gets kind of mind-bending. If the basic laws of physics don't care about the direction of time, but the outcome we see is just a statistical probability, is the arrow of time then just an illusion?
That is a fantastic way to frame it.
Yeah.
I mean, from a physics standpoint, nothing is stopping all the molecules of a scrambled egg from vibrating back into a perfect yolk and shell.
But they never do.
They never do.
Yeah.
Because you would literally have to wait longer than the entire age of the universe for that to happen randomly. It is statistically impossible.
So physics is symmetric, but statistics are very much not.
Precisely. And that's the key takeaway here. We can tell the past from the future for one reason and one reason only. The past was more orderly. Time is the measure of things falling apart.
Okay, so if entropy is always increasing, if the messiness always wins, where does that road end? What's the ultimate fate of the cosmos?
Well, that leads us to the pretty chilling concept known as the heat death of the universe.
Heat death.
Yeah. Eventually, entropy will max out. All the usable energy will have been used, the stars will burn out, and all their heat will just spread evenly across space.
And when we say heat, we're not just talking about temperature, right? It's the difference in temperature that matters.
Exactly. All of our technology, all of life, even thought itself, requires energy gradients, something hot next to something cold. In the heat death scenario, the entire universe reaches a final, uniform, incredibly cold temperature.
No more gradients, no more structure.
Nothing. Just a thin, lukewarm soup of particles. All the engines of complexity, galaxies, stars, they just stop.
Yeah.
It's kind of amazing to think that we're living in this golden age right now, where there's still so much order left to power things like us.
That is a profound thought. The fact that our entire perception of forward motion, our lives from birth to death, is just driven by the sheer overwhelming odds of statistics.
It really is. So if the movement of time is defined by systems falling apart, let me leave you with a final thought to mull over.
Okay.
What highly structured system in your own life, a project, a routine, even a meticulously organized room, is currently feeling that inevitable statistical pull toward maximum entropy?
Welcome to the deep dive. Today, we're getting into something that happens every single time you use your phone or computer.
Yeah, we're talking about heat, but not just wasted electricity. We're talking about the fundamental, inescapable price of knowledge itself.
And our mission for this deep dive is to figure out how solving a paradox from way back in 1867 actually sets the ultimate speed limit for all modern tech.
That's right. We are diving into Maxwell's demon.
And our sources for this really frame it around a single powerful idea that information isn't just an abstract concept, it's physical. It behaves like energy.
It all comes back to the second law of thermodynamics.
Yeah.
The rule that says things in a closed system tend toward disorder. Entropy always increases.
Always. Okay, so let's set the scene. I want you to picture a box. It's perfectly sealed off from the universe.
And inside this box, you've got a gas, a mix of molecules. Some are moving fast, they're hot. Others are slow, they're cold, all just bouncing around randomly.
And then there's a wall right down the middle, splitting the box in two. And in that wall, there's a tiny, frictionless, weightless little door.
And this is where our demon comes in. He's a tiny, intelligent gatekeeper.
His only job is to watch that door.
Exactly. And his whole purpose is to violate that second law we just mentioned. So when a fast, hot molecule comes at the door from the left side,
He opens it, lets it through to the right.
and when a slow, cold one approaches from the right side, he makes sure it gets trapped on the left.
So over time, he's just sorting fast ones to the right, slow ones to the left.
Until the right side of the box is genuinely hot and the left side is genuinely cold. He's created a temperature difference. He's created order out of chaos.
And he did this without performing any work, right? He just opened and closed a weightless door. He didn't push or pull anything.
That's the paradox. That's what confused physicists for about 100 years. He seems to have reversed entropy and created usable energy for free, which should be impossible.
A universe that's more ordered than it was before with no cost. So how on earth did they finally, exercise this demon?
Well, the breakthrough came when they stopped looking at the thermodynamics of the gas and started looking at the demon himself. The answer was in a totally different field.
Which was?
Information theory. Think about it. To sort the molecules, the demon has to know which ones are fast and which are slow.
He has to measure them.
He has to measure them. Is this one fast? Yes or no? That decision, that piece of information has to go somewhere.
Into his brain, his memory.
Precisely. He has to keep a running list. Fast, slow, slow, fast, fast.
Okay, but why is that a problem? Couldn't you just have an infinite memory, a giant hard drive?
But memory isn't abstract. It's a physical thing. It takes up space. Eventually, to keep sorting new molecules, his memory fills up.
So he has to make room. He has to delete the old data.
He is forced to erase his memory.
Yeah.
And that right there is the hidden cost. This brings us to a crucial idea called Landauer's principle.
I feel like this is the punchline.
It is. Landauer's principle states that erasing a bit of information isn't free. It's an irreversible physical process. And forcing a physical system to forget something, to go back to a zero state, must release a minimum amount of heat.
Wow. So the energy it costs him to forget the information
Is greater than the energy he gained by sorting the gas in the first place.
So the whole system, the gas plus the demon's brain, is actually becoming more disordered. Entropy still wins.
Entropy always wins.
Yeah.
The demon was paying a cosmic processing fee the whole time and didn't realize it.
And what's so incredible about this is what it proves. Information is physical. A 1 or a 0 isn't just an idea, it's a physical state of a system.
And that principle sets the absolute rock-bottom thermodynamic limit on how efficient any computer can be.
Which brings it right back to you listening to this. That heat coming off your laptop isn't just waste from the power supply.
No. Every time your computer flips a bit, overwrites a piece of data, it must, by the laws of physics, generate a tiny bit of heat. It's the cost of thinking.
So the demon ultimately failed because the act of measurement and, crucially, the erasure of that information created more disorder than his sorting ever fixed.
You just can't know something for free. There's an energy price tag for knowledge itself.
Which leaves you with a pretty staggering thought.
If this tiny demon failed just because he had to forget a list of molecules, what is the total entropic bill for trillions upon trillions of bits of data our entire world now creates, stores, and erases every single day? Welcome to the Deep Dive. Today, we're going to get into a way of measuring civilization that completely ignores culture, politics, art, all of it.
It does. Our sources describe it very simply. Energy is the currency of reality.
And if energy is the currency, then we need a way to measure that wealth, right?
Exactly.
Yeah.
And that tool is the Kardashev scale. It was developed by physicist Nikolai Kardashev, and it's this system for classifying civilizations based purely on, the amount of energy they can control.
It's a fascinating lens. Suddenly, all our sci-fi ideas about aliens sort of snap into focus.
They really do. They fall into 3 very clear tours.
Okay, so let's start at the beginning. Type I. What does that actually mean?
Type I is a planetary civilization. They command all the energy available on their home planet.
All of it. So you mean every bit of sunlight that hits the surface?
Every photon. Plus all the wind, the tides, full control over geothermal energy. They've completely mastered their planet.
Which brings us to the big question. Where are we on this scale? I've seen the numbers 0.73, which sounds pretty close.
It sounds close, but the scale is logarithmic. So that gap between 0.73 and 1.0 is actually immense.
It's not just the last few steps then.
Not at all. It's a huge leap. And the fundamental reason we're stuck, according to the sources, is our reliance on combustion. We're still burning dead plants, fossil fuels.
Right. We haven't mastered our own systems yet. We don't control the weather or the geology.
We're still basically just playing with fire. The predictions say we might hit type I in maybe 100 to 200 years.
Okay, but let's scale up. What happens after a civilization graduates from the planetary nursery? What's type 2?
Type 2 is the stellar civilization. They've moved beyond the planet entirely and now capture the total energy output of their home star.
The whole star. I mean, how is that even possible? The classic example is the Dyson sphere, right?
That's the one. It's this theoretical megastructure, basically a shell of solar collectors completely surrounding the star, capturing everything.
Wow. So with that kind of power, you're talking about, well, virtually infinite energy.
Pretty much. A Type 2 civilization would be immune to most natural extinction events. They could terraform other planets, power interstellar fleets. It's a whole new ballgame.
And then there's the peak, the absolute top of the scale, Type 3.
The galactic civilization. Now you're not just controlling a planet or a star, you are harnessing the energy of an entire galaxy.
Billions of stars.
Billions. Our sources say they would seem like gods to us. They could manipulate black holes, travel instantly across the galaxy, maybe even change the laws of physics in their local area.
Which leads us to this huge, glaring problem. If these godlike civilizations are possible, and energy is the currency of reality, why is the universe so quiet?
That is the core of the Fermi paradox, the great silence.
Because we should be able to see them, shouldn't we? All those Dyson spheres should be glowing with heat.
They should be everywhere, but we look out and we see nothing. Just silence. And that silence forces us to consider something called the great filter.
The great filter, this idea that there's some barrier that stops life from getting to type 2 or 3.
And the potential filters our sources list are, frankly, terrifying. Nuclear war, runaway climate change.
Or just the possibility that intelligent life is a 1 in a trillion mistake.
And this is where it all comes back to us right now. The source material has this incredibly sharp analogy for our current stage.
I know the one you mean. We're babies playing with matches in a wooden house.
Exactly. The matches are fossil fuels, but it's more than that. We have developed Type 3 weapons nuclear bombs with Type 0 wisdom. That gap is the real danger.
So this transition, this climb from 0.73 to type 1 is what the source calls the most dangerous test a species can face.
It is. We are stuck right in the middle of it. We're fragile.
The Kardashev scale then isn't really about aliens, is it? It's a mirror.
It's a mirror reflecting our own existential challenge.
So the final question we want to leave you with is this. Is the great filter behind us in the deep past of evolution? Or is this type I hurdle climate, conflict, our own energy sources, the filter itself? Are we living through that test right now? Something to think about. Welcome to the deep dive. Today, we're going straight into, well, what our source material calls the most disturbing experiment in history.
That's not an exaggeration either.
No, it really isn't. We're tackling the double slit experiment, and our mission here is to unpack this truly bizarre idea that reality itself seems to change the moment you look at it.
It's a big one.
So, to get our footing, let's start with something we can all picture, the normal world.
Right, the classical world.
Imagine you're throwing tennis balls at a wall, and in that wall there are 2 vertical slits.
Okay.
On the back wall, behind the slits, you'd get what? 2 vertical bands of marks where the balls went through?
Exactly. 2 bands. The ball goes through slit A or it goes through slit B. Simple. Predictable.
That's where the simple part ends.
That's where it ends. Because the second you swap out those tennis balls for something quantum, like light or even a single electron,
everything goes haywire.
Completely. You don't get 2 bands anymore. Instead, you get this series of many bright and dark stripes, an interference pattern.
And that pattern, the stripes, that's the dead giveaway, isn't it? That's wave behavior.
That's the smoking gun. It proves the electron is acting like a ripple on a pond. It's going through both slits at the same time and then interfering with itself on the other side.
Okay, interfering with itself, that's already strange.
Yeah.
But this is where the sources push it further and it gets even stranger.
Oh, yeah.
They thought, all right, what if we slow it down? We shoot just one single electron at a time.
Right, one particle.
Logically, it has to choose now. It must go through slit A or slit B. It can't interfere with itself if it's all alone.
That is what common sense would tell you. But that is not what happens.
No.
Even firing them one by one, over time, that same exact interference pattern builds back up again, dot by dot.
Wait, how? The single particle is still interfering with itself?
Somehow, yes. Before it's measured, the electron isn't in one place. It exists in a state of superposition.
A cloud of probability.
You got it. It's going through slit A, slit B, both, and neither. all at the same time, just a wave of possibilities.
So naturally, the next step for the experimenters was to try and cheat.
To catch it in the act.
Exactly. They put a tiny little detector right next to the slits to see which path the electron actually takes.
And this is the moment everything changes. The act of measurement.
What happened?
The instant that detector is turned on, the interference pattern vanishes. It's just gone. And you're left with two solid bands, just like the tennis balls.
Wow. So just by looking at it.
Just by looking at it, we force the wave of possibilities to pick one. We cause the wave function to collapse. Our observation isn't passive, it's an intervention.
So the big, profound takeaway here for all of us is what? The universe isn't really there until we look.
In a way, yes. At this fundamental level, matter seems to exist only as a cloud of probability. It only solidifies into a definite reality when an observer observes.
That is genuinely disturbing. It kind of challenges everything you assume about the world.
It does. It's why Einstein had such a problem with it.
Well, a huge thank you for supplying the sources that led us down this very, very deep rabbit hole.
Of course. And here's maybe one final thought to leave you with.
Okay.
If the act of looking solidifies reality from a haze of possibilities, what goals or ideas or future paths in your life are just sitting there right now in that unmeasured cloud of probability? What's just waiting for your conscious attention to make it real? Something to ponder.
Today we are wrestling with a topic so fundamentally weird that Albert Einstein himself called it spooky action at a distance.
That's right.
We're taking a deep dive into the source material around quantum entanglement, really trying to peel back the layers on physics' most famous paradox.
And our mission today is to get past the basics pretty fast. We want to distill exactly why it's so spooky and, understand the catch that stops it from being a magic telephone.
Right, and then explore how this bizarre quantum bond is actually changing things in the real world, specifically security.
Exactly.
So, okay, let's start with the core definition. Entanglement. It happens when two particles interact and they become, linked. They share a single mathematical reality, a wave function.
They essentially lose their individual identities. They're tied together no matter how far apart they get.
So that shared identity means their properties are perfectly correlated.
Perfectly. If we look at the source material on particle spin, for instance, imagine you have two of these entangled particles. You measure particle A and find it spinning up.
Then particle B has to be down.
It must be spinning down. There's no other option. It's required to keep the whole system balanced.
Okay, and this is where it gets really, really puzzling.
Yeah.
Let's take those two particles and separate them by some just immense distance.
1 billion light years, doesn't matter.
1 billion light years. So you measure particle A right here on Earth, you see it's up instantly.
Instantly, that's the key word. Particle B, all the way across the universe, just becomes down.
There's no delay.
No measurable time delay at all, and that's the issue. The information about particle A's state seems to get to particle B faster than the speed of light. It seems to violate, everything we know.
So that's the obvious question then. If one particle state instantly affects the other, why don't we have an instant telephone to the stars? Why can't we, text someone on an exoplanet?
And that is the crucial caveat in all the source material. It's a fantastic question. The universe kind of protects itself from this with one simple fact: randomness.
Randomness.
Yes. While you know for a fact that B will be the opposite of A, you can't force A to be up or down. When you make the measurement, the result you get is completely probabilistic. It's a coin flip. You can't control it.
So that's the catch. You can't encode a message. You can't decide to send a 1 or a 0 because you don't know if you're going to get an up or a down until you've already measured it.
Exactly. The analogy in the source is great. It's like having two magic coins that when you flip them, they'll always land on opposite sides.
But you can't choose which one lands on heads.
You can't choose. So you can't use it to send a code. You both just get a string of random, albeit perfectly correlated data.
Okay, so paradox solved. No faster than light communication. But if we can't control it, how is this useful? How does this randomness become a feature?
Well, this is where it gets really clever and where the sources point to quantum key distribution, or QKD.
For security.
For security, it turns the biggest weakness of entanglement, its fragility, into its greatest strength. It becomes the ultimate bug detector.
How does that work? If a hacker, say, tries to spy on the particles as they're traveling between two parties.
The very act of them trying to measure the particle to look at it breaks the entanglement.
It just shatters the connection.
It collapses the wave function. The particles lose that perfect correlation, so the person on the receiving end immediately knows something is wrong. They can check a few of the particles, see that the up-down correlation is no longer perfect, and realize the line isn't secure.
So the very act of eavesdropping destroys the information being sent. The fragility becomes a firewall.
An unhackable firewall. You know instantly that someone has tried to listen in.
Wow. We've really gone from Einstein being skeptical about spooky action to using that same spookiness for, instant physically guaranteed security.
It's an incredible journey. And here's, I think, the final thought to really leave you with, the thing that all this work implies on a deeper level. Entanglement suggests that our whole concept of distance, of space, might just be an illusion of our classical world. In the quantum realm, these particles aren't really far apart. They are still, in a very real sense, part of the exact same system.
So distance doesn't exist for them.
It's as if, on the most fundamental level of reality, there's no distance at all. Welcome to the deep dive. Today, we're getting into something that really bends the mind. Quantum computing. And our mission here is to make one thing crystal clear. A quantum computer is not just a faster supercomputer. It's something else entirely.
Exactly. And to really get that, I think we have to start small, like at the smallest piece of information.
The bit.
The classical bit. In your phone, your laptop, it's a tiny switch. It's either a 0 or it's a 1. That's it. Simple.
Definitive. But the quantum version, the qubit, that's where the rules of the game just, completely change.
They absolutely do, because a qubit isn't forced to make that choice. It can exist in what we call a superposition.
Which means?
It means it can be a 0 and a 1 at the exact same time. It's in this fuzzy state of all possibilities at once, right up until the moment you actually measure it.
Okay, so that immediately changes how much information you can hold. If I have, say, 3 normal bits, I can store 1 number.
Right, 1 3-digit binary number at a time. But with 3 qubits, you're holding everything simultaneously. All 8 possible combinations, from 000 all the way to 111. They're all there at the same time in one system. The power just scales exponentially.
And that scaling leads to a stat that our sources point out, which just sounds like science fiction. You're saying that a quantum computer with only 300 stable qubits could hold more possible states than there are atoms in the entire known universe.
It's almost impossible to visualize, but yes, that's the power we're talking about. We're leveraging the fabric of reality to hold information.
So how does a machine like that actually calculate anything? If it's not just checking answers one by one really, really fast, what's it doing?
Okay, so think of a super complex maze. A classical computer would try one path, hit a dead end, go all the way back, and then try the next path.
One at a time.
Sequentially, yes. A quantum computer, because of superposition, essentially sends a version of itself down every single possible path in the maze simultaneously.
So how does it find the right answer? Wouldn't it just be a chaos of information?
This is the most elegant part. It uses a property of waves called interference.
Like ripples in a pond.
Exactly like that. Think of all the wrong answers as waves. When their paths cross, a peak meets a trough, and they cancel each other out, they just vanish.
That's destructive interference.
Precisely. But the paths for the correct answer, their waves amplify each other. A peak meets a peak, and it gets bigger and bigger. That's constructive interference.
So it's not finding the right answer so much as it's silencing all the wrong ones.
That is a perfect way to put it. The correct solution is the only thing left shouting at the end of the calculation.
Which all sounds incredible. But, of course, there's a catch. We're in what the sources call the NI-skew era, right? Noisy intermediate scale quantum. What does noisy mean here?
It means the qubits are unbelievably fragile. They're so sensitive. A stray microwave, a tiny change in temperature, anything can knock it out of that delicate superposition.
It decoheres.
It decoheres. It collapses back into a boring old 0 or 1, and your quantum calculation is ruined. That's the engineering challenge of our time.
But assuming we solve that, when these machines are stable, what kind of problems are we looking at solving?
Problems that are simply impossible today. Things like developing new medicines by simulating molecules perfectly or creating new materials. And of course, the big one.
Breaking encryption.
A stable quantum computer could solve problems in seconds that would take our best supercomputers, quite literally, 10,000 years to figure out.
So the takeaway really is that this isn't about a faster clock speed. The power is from operating in that superposition, exploring all probabilities at once.
and then using interference to let the universe itself cancel out all the wrong paths.
So if we're leaving our listeners with one final thought to chew on,
I think it's this. A classical computer manipulates ones and zeros. A quantum computer calculates by manipulating the fundamental probabilities of reality itself. So the question becomes, what are the limits of computation when your machine is speaking the same language as the universe? All right, welcome back to the Deep Dive. Today we are jumping into something really fundamental. We're talking warping the grid.
That's right.
Specifically, time dilation, and the big one, the universal speed limit.
Yeah, and our mission here is to really get into how the basic rules of motion we all, take for granted just completely fall apart when you get close to the universe's ultimate speed.
And what that forces us to rethink about time itself.
Exactly. Something we all assume is, constant.
Okay, so let's start with something relatable, something that makes sense in our daily lives.
Good idea.
Speeds add up. Simple. If you're on a train going 50 miles per hour and you run forward at 10, then relative to the ground, you're going 60.
Right. Intuitive. But now let's introduce light. Light travels at c. That's the universal speed limit. And here's the core puzzle our sources point to.
Okay.
If you're on that same 50-mile-per-hour train and you shine a flashlight forward, the light beam does not go c plus 50.
Wait, hold on.
It still goes exactly c.
But
Anything.
Why? That makes no sense. Everything else adds up. Why is light the exception?
Because Sine isn't just a speed. It's a fundamental property of the universe. It's the speed of causality. So for the speed of light to be the same for everyone, no matter how fast they're moving,
something else has to change. Something has to give.
Precisely. And that something is time and space. This is where we get to time dilation.
Okay.
Put simply, the faster you move through space, the slower you move through time.
And this is where that just staggering example comes in, the one that really grounds it.
Go for it.
If you, the person listening, got in a ship and flew at 99% the speed of light for just 1 year, your calendar year, you'd come back to Earth and find 50 years had passed.
Yeah. And we have to be crystal clear about what this means. This isn't just, a feeling or some kind of perception trick.
This is the twin paradox.
This is the twin paradox. The twin who takes that trip is physically, biologically younger. Their cells have divided fewer times. Their watch has ticked fewer seconds. Time is not a universal clock in the background. It's a personal river.
A personal river, wow. So its flow depends on how fast you're moving.
Your velocity dictates your personal flow of time.
So what's the actual mechanism here? What connects my speed in space to the slowing of my own personal time?
It all comes down to one unifying idea, the big aha moment.
Okay, I'm ready.
You are always traveling through space-time at the speed of light.
Always, even when I'm sitting still.
Even right now, sitting still, think of it like a fixed budget, a speed budget.
A speed budget, I like that. So I have a total speed of c to span across space and time.
Exactly. When you're sitting still, you're using 100% of your speed budget to travel through the time dimension. You're aging at the maximum possible rate.
So you're rushing into the future.
In a way, yes. But the moment you start moving through space, say, getting on that rocket, you have to divert some of that speed. You take it from the time axis and apply it to the space axis.
And because the total budget has to stay at c, my travel through time has to slow down to compensate.
It has to. You can't exceed c in space-time because you're already going c. You're just redirecting your velocity.
So to boil it all down, my speed through space determines the speed of my clock.
That's the core takeaway. Time is completely relative to your motion.
Which, okay, leaves us with a final, pretty wild thought for you to chew on. If time is really just your speed budget being diverted from movement in space, what would happen if you could be perfectly, absolutely still? If you could dedicate that entire budget to just the time axis, what is the fastest possible speed you could age? Welcome to the Deep Dive. Today, we're going to take on gravity.
And not in the way you might think.
No, not at all.
Oh.
We're going to try and, completely redefine that physics lesson you got back in high school.
The idea that gravity isn't a force at all, that it's really just geometry.
And the most incredible takeaway, the thing that just grabs you right away from the source material, is this. The reason you're sticking to the floor right now isn't a pull from the earth.
Right.
It's because you are, and this is a quote, sliding down a massive dent in the universe.
I love that phrasing. It's so perfect.
So let's try and understand that dent. First, we have to start with the old idea, the comfortable one.
Newton.
Sir Isaac Newton. For him, it was all pretty straightforward, wasn't it?
It was. Gravity was a force, an invisible pull between two objects.
Like an invisible rubber band stretching between the Earth and the Moon. Just a pull.
A straight pull, exactly. But what Einstein did with general relativity was, well, it was so much more elegant.
He said that whole force idea was just, what, an illusion?
Basically, it's not a force you feel, it's a condition of the universe you're moving through. It's the literal shape, the curvature of space-time itself.
Okay, so how do we even begin to visualize a curve in space-time?
Well, there's that classic analogy for a reason. The trampoline.
Right, the bowling ball on the trampoline.
Yeah.
You put a massive object, like a planet, onto this stretched fabric.
And the fabric, in this case, is the four-dimensional grid of space-time, yeah.
And it just sinks down, creating this big curve.
Precisely. Now, if you roll a little marble past it...
It's not being pulled by the bowling ball?
No. It's just trying to go in a straight line, but the surface it's on is now curved. Its path is redirected by the geometry.
You keep saying space-time, the 4D grid. We can picture the three dimensions of space, but where does time fit in?
That's the crucial part. They're woven together. That straight line the marble is trying to follow.
A geodesic. Right.
That geodesic is its path through all four dimensions. From our three-dimensional view, it looks like a curved orbit around the planet.
But from the marble's perspective...
It's just coasting. Straight ahead. The curve is baked into the fabric of the universe itself.
So, okay, if it's the geometry and not a force that acts on mass, what happens when something with no mass at all hits that curve? I mean, like a beam of light.
That is the exact question that proved the whole theory.
It should still be affected, shouldn't it?
It has to be. And it is. We see it all the time. It's called gravitational lensing.
Right. So light from a star way off in the distance passes by a massive galaxy.
And the light simply follows the contour, the curve in space that the galaxy's mass has created.
So it bends.
It bends. And because of that, we can actually see stars that are physically behind the galaxy. The light curves around it and comes to us.
That's incredible. So what's the most extreme version of this? When the curve is so deep that the trampoline just rips.
That's a black hole. That is the ultimate expression of this geometry.
And it's not a cosmic vacuum cleaner.
Not at all. It's what happens when the curvature becomes, well, effectively infinite. The geometry folds in on itself so tightly
that the path out just vanishes.
It literally ceases to exist. And here's the wildest part where space and time really show their one thing.
Okay.
Inside that point of no return, the direction we all understand as the future no longer points forward in time.
Doesn't.
No. It physically points toward the center of the black hole. You are, quite literally, falling into your own future.
Wow.
So it all comes down to that one perfect phrase.
Go on.
Matter tells space how to curve. Space tells matter how to move.
The geometry is everything.
It's everything.
So a final thought for you as you're sitting there feeling what you think is the pull of the Earth.
But which is really just a curve.
Exactly. If all motion is just following these curves in the universe, and in a black hole, the future is a physical direction pointing inward.
Where does that leave us?
Yeah. Where exactly is your future pointing right now?
So for today's deep dive, we're looking at your research on something we all use constantly, GPS.
We are.
And our mission really is to show how finding, the nearest coffee shop is actually a direct result of Einstein's work.
It really is. I mean, the whole setup is just incredible. You've got these satellites about 20,000 kilometers up.
Right.
And your phone needs to hear from at least 4 of them to figure out where you are. The timing has to be ridiculously precise.
And that's the key, right? The precision, because light travels about a foot in a nanosecond.
Exactly. So if your clock is off by just a few nanoseconds, the system suddenly thinks you're across town. It's that sensitive. Which
is just wild. It makes GPS, the only consumer tech out there that absolutely needs both special and general relativity to even work. It's like this double whammy of physics.
It is a total double whammy. The first part, that's special relativity.
Yeah.
That's all about velocity.
How fast things are moving.
Exactly.
Yeah.
And these satellites are moving fast. We're talking 14,000 kilometers an hour. And because of that speed, their clocks, their atomic clocks, actually tick a tiny bit slower than ours down here on Earth.
Slower. By how much?
By about 7 microseconds every day.
Okay, so that's the speed side of it. Time slows down. But then there's the other whammy, general relativity, the gravity part.
Right.
But wait, why does that even matter? They're 20,000 kilometers away from Earth. Isn't gravity, pretty weak up there?
It's weaker, yes, but it is absolutely still a factor.
Yeah.
General relativity tells us that gravity actually warps space-time.
It bends time itself.
It does. And since the satellites are in weaker gravity, time for them moves a little bit faster than it does for us.
Oh, interesting. So it's the opposite effect.
It's the opposite, and it's much stronger.
Yeah.
That effect speeds their clocks up by 45 microseconds a day.
Okay, let me get this straight. So the satellite clocks slow down by 7 microseconds because of their speed, but they speed up by 45 because of the weaker gravity, so you net that out, and they're running fast by 38 microseconds every day.
That's the one. 38 microseconds too fast. And that sounds like nothing.
It sounds tiny.
But for GPS, it's a catastrophe.
Huh.
If you let that tiny error build up, your location would be off by 11 kilometers.
11 kilometers.
Almost 7 miles.
Yeah.
Every single day. Your phone would tell you the coffee shop is in the next county over.
So the whole system would be useless. So how on earth did they fix it? That feels like an impossible problem to solve.
The amazing part is they fixed it before it even left the ground. It wasn't some software update they pushed later.
No.
The engineers literally took Einstein's theories, did the math, and built the clocks from the very start to tick just a little bit slower on purpose.
So they pre-corrected for relativity, they built the flaw in to make it work perfectly in space.
They baked the solution right into the hardware. They trusted the physics that much.
That's incredible. So what this means for you listening right now is that every time you use Google Maps, you're not just getting directions. You are actively confirming Einstein's theories of the universe.
You are. You're using the fact that the fourth dimension, time, can be stretched and squeezed just to do something as mundane as finding a Starbucks.
It really reframes the whole thing.
It does.
Yeah.
And here's a final thought to take away. If navigating our streets now requires us to account for the warping of space-time, what happens next? What other everyday tech is just around the corner that will force us to use, say, the weirdness of quantum mechanics just to get through our day? Welcome to the Deep Dive, where we get you up to speed on the big ideas. So today, we're going to talk about something we all use every single second, the internet. But specifically, we're asking, where is it? I mean, physically, we all say our data is in the cloud.
Right, which is, fantastic marketing. It sounds so light and ethereal.
Exactly. But it's not really true, is it? Our sources point to a very different reality.
A much more physical one. The immediate takeaway is pretty stunning, actually. The internet isn't in the sky. For the most part, about 99% of international data is under the ocean.
Under the ocean.
Yeah.
Traveling through these incredibly thin strands of glass fiber optics.
That's it. That's the true, tangible backbone of the whole thing.
Which is just an unbelievable engineering problem. So
Yeah.
How do you trap a beam of light inside a wire thinner than a human hair and get it across an ocean?
Well, it comes down to a really elegant piece of physics called total internal reflection.
Total internal reflection.
The best analogy I've seen is to think about skipping a stone on a lake.
Oh, yeah, I can picture that.
So if you throw the stone at a steep angle, it just breaks the surface and sinks, right?
Right, the light would escape.
Exactly. But if you throw it at a really shallow, glancing angle, it bounces perfectly off the surface, skips right across.
And that's what the laser is doing inside the glass.
Precisely. The cable has this core of ultra-pure glass, and it's surrounded by a slightly different glass called cladding. The laser goes in at such a shallow angle that it just keeps bouncing off the walls perfectly for thousands of miles. Not a single photon gets out.
Okay, so that solves the hardware. The light stays in the glass.
Yeah.
The light is just on or off, binary.
Mm-hmm.
How do you push the entire planet's data, every movie, every transaction, down a single hair-thin strand without a colossal traffic jam?
That's where it gets even cleverer. You're right. If we only sent one signal, it would be a massive bottleneck. So we use an advanced technique. The term is wavelength division multiplexing, WDM for short.
Wait, you're sending different signals down the same fiber. How do they not just crash into each other and become chaos?
That's the beautiful part. They don't interfere because they're different colors of light.
Different colors.
Yep. We send a data stream on red light, another on blue, another on green, and dozens of other shades all at the same time down the same fiber.
So you're literally sending rainbows under the sea.
We are literally sending rainbows of information. It multiplies the capacity exponentially.
The scale of that must be just staggering. What kind of speed are we talking about?
A single strand can carry about 100 terabits per second.
Which in real-world terms is like what?
The sources say that's enough bandwidth to transmit the entire Library of Congress, every book, every document, in just a couple of seconds.
That's almost impossible to comprehend.
It is. But there's a small catch,
Yeah.
a physical limit. Light in glass is actually about 31% slower than light in a vacuum.
31%. That sounds like a lot.
It is, especially when nanoseconds matter. For, say, algorithmic trading in finance, that tiny delay is why banks will spend billions to lay a new cable on a slightly shorter, riskier path. That 31% is arguably one of the most expensive factors in modern finance.
So you have this incredible, super fast system, but it's also incredibly fragile. I mean, it's just a cable sitting on the ocean floor.
Absolutely. We think of data as being safe and untouchable, but these things are vulnerable to fishing trawlers, ship anchors, and even, shark bites, surprisingly.
Shark bites, you're kidding.
Nope. The whole digital world rests on something very physical and very easy to break.
So the final takeaway here, what's the big picture?
It's that we've essentially wrapped the entire planet in a nervous system. A complex, sensitive nervous system made of glass, pulsing with the light of a million lasers.
Right. Tangible.
Physical.
Not a cloud at all. So here's the thought to leave you with. You started this thinking your data lived up in the sky. Now you know it's in a massive, fragile network of glass at the bottom of the ocean. So what other assumptions that we hold about our digital reality might be worth questioning next? Something for you to mull over until our next deep dive.
So, when you think of the cloud, right, you probably picture something abstract, maybe even effortless.
Weightless, almost.
Exactly. But for today's deep dive, we're getting into the wet, heavy, physical reality of what makes it all work.
The undersea internet cables.
And here's the core idea that it's amazing. The entire backbone for the global economy, for all our communication, relies on a cable that's about the size of a garden hose?
Pretty much, yeah.
Okay.
And what's fascinating is where they put them. If you pull up a map of these cables, it almost perfectly mirrors the old 19th century trade route.
No way.
Oh, yeah. It connects all the same key hubs, London, New York, Tokyo, Singapore, and they're laid by these huge ships that literally just drag a plow across the ocean floor.
Just digging a trench in the seabed?
It's brute force, really.
So once this relatively thin garden hose is down there, it's not exactly safe. It runs into some really unexpected threats.
Mm-hmm.
And we have to start with the most bizarre one. Sharks.
The shark problem. It's a classic. They used to bite the cables all the time.
Why? Were they just curious?
Well, the theory is they were sensing the electromagnetic field from the power running through the cable.
So what did they do? I mean, how do you stop a shark from biting a cable?
That's largely a solved problem now, thankfully. They just wrap the cables in Kevlar.
Like the stuff in bulletproof vests.
The very same. It's perfect for resisting that kind of abrasion, whether it's from a shark's jaw or just rubbing against rocks.
Okay, so the shark story is great, but that's not the real enemy, is it? The biggest threat is actually, well, it's way more boring.
It's fishing trawlers.
Right. Just dropping an anchor in the wrong place. That's the number one cause of these cables being cut.
It happens all the time, which, it really makes you think. If it's that easy to do by accident.
Oh, what happens if someone does it on purpose?
Exactly. In any modern conflict, cutting an enemy's internet cables is the new strategic move. It's like blockading a port. You cripple commerce, communication, everything.
And that vulnerability comes right back to the design itself and this constant need for power. The data is just
light, right?
Pulsing down these tiny glass fibers.
Light fades over distance. It gets weaker and weaker.
So how do you keep it going across an entire ocean?
You need to boost it. All along the cable on the ocean floor, they have these things called repeaters. They're basically just powered amplifiers.
And how often do you need one of those?
About every 50 miles or so.
Wow. So they all need electricity thousands of miles from anywhere.
Mm-hmm. And that's the other key part of the garden hose. Wrapped around those delicate glass fibers is a copper conductor.
To carry the power.
And carries a shocking amount of it. We're talking up to 10,000 volts running across the ocean floor.
10,000 volts? I mean, is that a danger? If it breaks, does it just electrocute everything around it?
You'd think so. But the voltage is really just there to push the current over such a huge distance. If there's a serious break, it shorts out almost instantly. The real danger isn't an electrical shock.
It's the blackout.
It's the data just vanishing instantly.
So let's bring this all together for you. That smooth, seamless thing you call the cloud.
Yeah.
It's not abstract at all. It's a wet, heavy, high-voltage garden hose sitting in the mud at the bottom of the Pacific.
I mean, the physical reality of it is stunning, and its fragility is something we totally overlook.
Absolutely.
So the next time you're on a video call or you're just sending an email, remember that. Your connection depends entirely on that 10,000-volt lifeline, which is constantly at risk of being snapped by something as simple as a ship's anchor. Our whole digital world is built on something you could sever by accident. Okay, so let's get into this deep dive on high-frequency trading. The sources we looked at all point to this this incredible arms race, a race to, well, to literally buy time. The core idea is just fascinating, that in finance today, your profit is dictated by how close you can get to the speed of light.
It really is. The foundational principle is that information is profit. I mean, think about it. If you know the price of Apple stock is going to change in New York just 1 millisecond before someone in Chicago knows,
You have a guaranteed winning trip.
you have a guaranteed win. And that single idea, that's what kicked off these speed wars.
So our mission here is to unpack the wild engineering feats that came out of that simple quest for speed.
And the first enemy they had to fight was, the medium itself, the cables.
Right, the fiber optic cable.
Exactly. The basic physics problem is that light moves about 31% slower through glass than it does through air.
And that 31%, that's not a small number when billions are on the line.
It's a huge liability. That delay, that tiny little bit of latency between, say, New York and Chicago, that was costing firms millions.
So the solution wasn't better glass. The shocking part is that they just got rid of the medium.
They went around it. Yeah.
We learned they started building these massive private chains of microwave towers.
Yeah.
Just huge engineering projects to beam the signal through the air.
Because microwaves travel through the air at, pretty much the speed of light, speed c.
And what was the payoff for all that construction?
It was immediate. That switch saved about 4 milliseconds on a round trip.
4 milliseconds.
Which sounds like nothing, but in the early 2010s, that tiny advantage was valued in the billions. That gives you a sense of the scale we're talking about.
Okay, so if 4 milliseconds was worth billions, where are we now? We have to talk about the nanosecond frontier.
Right.
This is where it gets really mind-bending. The next phase is almost poetic. After they conquered the air, they decided to put the air back inside a cable.
The hollow core fiber. It's a really elegant solution, actually.
Explain that.
It's a glass cable, yes, but there's a tiny air-filled hole running through the middle. So the light travels through the air, not the glass.
So you get the speed of microwaves?
With the bandwidth and the reliability of a traditional fiber cable. The best of both worlds.
And the speeds are just, they're not human.
Not even close. I mean, your reaction time, humans, is maybe 200 milliseconds. A good one. These HF algorithms, they execute a trade in 500 nanoseconds.
I can't even comprehend that number. So it's not just about being faster anymore. Our sources say this has evolved.
It has. It's no longer just a race. It's what they're calling the prediction war.
The algorithms are actively fighting each other.
They're fighting. They're using tactical deception. We're talking about things like spoofing.
Okay, what is that?
So an algorithm will place a huge fake order to buy a stock. It has no intention of actually buying it.
Why? To trick the competition.
Exactly. The other algorithms see this massive order and they think, oh, the price is about to spike, so they all rush in to buy.
And then what happens?
And just as they reveal their strategy, the first algorithm cancels its giant order. Poof. It was just bait. It tricked the others into a bad position.
So speed is being weaponized to exploit the reaction time of other machines. It's an invisible, automated chess match.
It is. We've basically created this strange new ecosystem. It's an automated war zone of financial AIs operating at a speed we can't even perceive, let alone participate in.
So what's the core takeaway here for you, the listener?
Yeah.
This entire multi-billion-dollar effort, from microwave towers to air-filled cables, it's all about pushing physics to its absolute limit.
Yeah, all just to shave off nanoseconds of travel time for light.
So that one AI can trick another AI for a tiny, tiny edge on a stock trade.
And that brings up a really provocative thought to leave you with. If we know that billions of dollars are riding purely on milliseconds and nanoseconds, what happens to our idea of, a fair market? What does fairness even mean when guaranteed profit is determined only by your physical proximity to the speed of light?